This is a discussion of Activity 4 from the CF unit for Inquiry into Physical Science. We ran out of time to talk about this in class. You'll notice there are no summarizing questions in this activity because this activity is designed to give you practice at crafting and analyzing force diagrams and crafting explanations for some scenarios based on the principles that have been learned in this and the previous unit. So I'm going to talk through these scenarios. I highly recommend, if you have not actually done this activity, to pause this video, go through, answer all the questions yourself, and then use this video to compare your ideas to what I'm going to talk about. Obviously, it's up to you ultimately how you want to use this tool if it's something that you take advantage of. I'm also not going to write all of the explanations out. I'm more likely going to verbalize most of them in these situations. I may draw some diagrams, but I don't think you need to watch a video of me writing in poor penmanship on my page too much. So let's just talk about these explanations for these different phenomena. So explanation number one is asking students to craft a narrative explanation with an accompanying force diagram to answer the question, why does the puck gradually slow down as it moves across the ice? And so there is friction in hockey. If you've played any hockey, it's obviously played on ice to reduce the friction. But there is some friction there, and pucks will not just slide at a constant speed forever in an ice rink. So here are three different students' force diagrams for the puck. They've all got the same motion arrows on there, so that's not really any difference. What's different is the way that they have described the forces. Student A has a force of the stick on the puck and a force of friction. Student B has just a force of friction, and student C has a gradually decreasing force of the stick. Which of these is the most appropriate to use in this explanation? Well, I would discard student A for a couple of reasons. While the stick is pushing on the puck, there is absolutely friction during that time, but that's a time when the puck is speeding up. You hit the puck with your hockey stick to make it increase in speed. And so here I've got unbalanced forces. There's more force to the right. And when I have more force to the right, or an unbalanced force to the right, which is already the direction that an object is moving, that is going to be speeding up. So that force diagram is correct for the situation in which the hockey player is hitting the puck, but not afterwards. Um, and perhaps this student has held on to that idea that forces are transferred, which is not correct. Energy gets transferred between objects, but forces do not. Student C's diagram is also incorrect because they say there is a gradually decreasing force of the stick. Again, that seems to me like an energy transfer idea, but force is not transferred from the stick to the puck. It only happens while the puck is in contact with the stick. The actual most correct diagram here is from student B, that there's only one force in the direction or in the plane of motion, I guess, after the hit, and that is the force of friction that is opposite to the direction that the thing is moving. That's an unbalanced force situation with the unbalanced force acting against the direction of motion, so that is going to be consistent with something slowing down. It is not complete, in my opinion, because in any of these labels, they haven't identified the pair of objects that are interacting. So all these should say things like friction force on puck by ice and force on puck by stick. So they have not provided complete force labels in any of those. All right, here are three different students' narratives for this explanation. The initial hit is what starts the puck moving. After the hit, it gradually slows down because no forces are acting on it. What's problematic about that? Well, the problematic about it is it's inconsistent with the idea of force and motion. If there are absolutely no forces acting on something, then the rules that we've established say it can be moving, it just won't change its speed at all. And slowing down is a change in speed. So that requires some sort of unbalanced force. You can't have no force on something that is slowing down. Student E, after the stick has lost contact with the puck, only a frictional force acts on it, so it slows down. Um, I think that's correct, but it says that these are problematic in at least one way. And to me, the biggest problem here is identifying the direction of the friction force. If you have only a single force acting on an object, that single force can actually speed something up or slow something down. Or if you've done all the extensions, you also have seen that it can change something's direction. And so without identifying the direction of the friction force, that explanation is incomplete, along with missing the more general theoretical idea connecting the rate of change of speed to the strength of the force. Student F, during the interaction between them, the force of the stick was transferred to the puck and then gradually runs out as it moves. Because the force pushing it forward gradually runs out, the puck's speed decreases. Well, again, that's, to me, indicative of a student that has not clearly differentiated force ideas from energy ideas. Energy gets transferred from the stick to the puck. But we also don't think of energy as gradually running out. We instead say, as it slides across the across the ice, there is a contact interaction between the puck and the ice, and energy is transferred from puck to ice, increasing the thermal energy of both of those, which decreases the kinetic energy of the puck. So, all right, and then it says, write your own narrative for why the puck gradually slows down based on the force diagram you chose on the previous page. Well, if you go back to the force diagram we chose here, we could say something like, a puck is sliding across the ice. You're absolutely fine to just start it in motion. And then the more general idea would say, when there is unbalanced force on an object, the speed of that object changes. When the unbalanced force is opposite to the direction of motion, rather, the speed of an object decreases. And then perhaps finally, because the friction force between the puck and the ice is opposite to the direction that the puck is moving, this is an unbalanced force, and the speed of the puck changes, it decreases, and it slows down as it moves across the ice. All right, the second scenario they ask you to think about in here is taxiing a plane. When taxiing a plane around an airport before takeoff or after landing, the pilots use the engines to push the plane along the ground. The engines work in the same way that the fan units push on the carts that you have used. When the aircraft is standing still with the engines running slowly, the pilot increases the power of the engines to start the plane moving. But when the plane reaches the desired taxiing speed, he reduces the engine power again, but not to zero. Why is this? If you've never noticed this, next time you're on a plane, listen to the engine noise while it is taxiing along level ground. Your task is to explain why the pilot reduces the engine power once the plane has reached the desired taxiing speed. Answer the following questions should help you think about why this is. So, first, do you think a frictional force plays a significant role in this situation or not? Briefly explain your reasoning. My reasoning would be, yes, I think friction plays a significant role in this situation. Friction from the ground, and more significantly when you're flying, friction from the air. But there is significant friction between the ground and the airplane, which you have to push against if you want to make the airplane move across the tarmac towards the runway there. To start a plane moving and make it speed up, do the forces acting on it need to be balanced or unbalanced? Well, if I am at rest, the only way I can make it move is to apply unbalanced forces on there. And so something, in this case the engine, has to push harder on the airplane than the friction does, or else I won't go anywhere. And this is very much just like the couch situation from the previous activity. Once the speed of the plane has increased to the desired taxiing speed, to maintain that speed, do the forces acting on it need to be balanced or unbalanced? Well, now I'd want speed to not change. And if I want speed to not change, this is a situation where I want the forces to be balanced. Finally, what do your previous answers imply about the strength of the pushing force needed to start the plane moving and increase its speed versus the force strength needed to maintain a constant speed. So if I assume that the friction is constant in here, which is a bit of an approximation, then I have to have a stronger push to get the airplane moving than I do to maintain the motion of the airplane afterward. All right, so why does the pilot reduce the engine power when the plane has reached the desired taxiing speed? It wants two force diagrams. So airplane 1 and airplane 2. Okay. 1, well, the plane is increasing in speed. So I know that there is going to be a friction force on the plane. I'm going to say by the ground, because when you are on the ground and not moving, that's the major effect. You don't have a lot of air resistance at that time. So in order to get the plane moving, I have to have a force on the airplane by the engines. And that force has to be bigger than the friction force on the plane by the ground in order to get this thing moving. Now, the speed arrow is somewhat optional in this diagram because you could be thinking about the instant just when it started moving when the speed was actually still 0. Later on, though, it's already moving, but I still have that friction force. However, now I just want to maintain a constant speed. And to maintain a constant speed, I need balanced forces. So the force on airplane by engines is smaller than it was in the initial diagram. Again, I'm not going to write the narrative so that you have to fight your way through the chicken scratch, but I will try to describe a possible narrative explanation. I might say, when an airplane is at rest or taxiing on the ground, the forces that are important to its motion are the friction force on the plane from the ground and the force on the airplane from the engines. The force on the friction force on the plane pushes opposite to the direction that a plane is moving, while the force from the engines pushes in the direction that the plane is or will be moving. In order to get the airplane moving and change its speed, I need to have a net force on the plane with unbalanced forces and the stronger force in the direction of the motion. Therefore, the force on the airplane by the engines must be larger than the friction force on the plane by the ground. However, to taxi at a constant speed, I need balanced forces on the airplane, which means that the force on the airplanes by the engine just needs to match the size of the friction force on the plane by the ground so that the net force is 0 and the speed doesn't change. You can say it in many different ways, but almost all of these are drawing the diagram and then turning the diagram into some words in paragraph form. The third question on here, why does the bug get squished? As you are driving down the highway, you hit a bug with your windshield. How can you explain that the bug suffers more damage than your car does? So explanation number 3, when a bug hits the windshield of a moving car, why does the bug get squished while the car suffers no significant damage? To answer this question, assume your windshield exerts a force of 1 Newton on the bug in the direction that the car is moving. What is the strength and direction of the force that the bug exerts on the car, and why does the bug suffer more damage than the car does? Well, represent this using diagrams. So car, you drive an old car from the 1980s, and it has no windshield. No. And bug, right? So I'm not going to put the bug on the windshield, but they are interacting. This is a giant bug here, like in northern Minnesota or something. I don't know. So there's your bug, and it's going to run into the windshield. Well, they told you to assume that there is a force here that is 1 Newton. So this would be force on bug by car. And it told us that's 1 Newton of force. Well, what does Newton's third law tell us? Newton's third law tells us that if there is a 1 Newton force on the bug by the car, there has to be a force on car by bug, and that is also 1 Newton. Those are equal and opposite to each other. So what does that mean in terms of my explanation? Well, again, I'm not going to write the whole narrative here, but I would say something like, when you hit a bug in your car, the car exerts a force on the bug, well, the bug exerts a force on the car. Newton's third law tells us that these forces are equal to each other in size, but opposite in direction. However, I would also include in my narrative the other idea, the rate of change of speed equals the strength of force divided by the mass of the object that is feeling that force. So the forces are equal to each other and opposite. That's Newton's third law. But this, which is actually Newton's second law, says, okay, I apply 1 Newton force. Well, 1 Newton of force on my car, which has a mass of many hundreds of kilograms, is going to have very little impact on its speed. If you actually calculated that and took 1 Newton of force, and let's just say your car has a mass of 1,000 kilograms, well, then your rate of change of speed is 1/1000th of a meter per second per second. But the bug, let's say the bug has a mass of 10 grams, and that's probably a heavy bug, but if it has a mass of 10 grams, you took 1 Newton and you divide by that mass, the rate of change of speed that you end up getting is, let's see, 10 grams would be 100 meters per second, which is 10 times the acceleration due to gravity. It's like when you hear people talk about g-force of acceleration, that's 10 g's of acceleration, which people can survive in certain orientations, but you are not likely to survive. And the bug doesn't survive this. In fact, the smaller the mass of the bug, the larger the bug's rate of change of speed. And there is some rate of change of speed which the bug cannot withstand, and the bug ceases to exist in living form as a result of that. Finally, they give you this scenario about you are the expert witness. Hopefully, again, you tried this experiment with the stuff in your science kit. As written in here, we do it with a cart and track. But you can do this with something on a Hot Wheels car. You can even do it with an index card and a coin. But the passenger is suing a bus company for injuries she claims were sustained when the bus had to brake sharply to avoid hitting an obstruction in the road. The passenger was seated in the row of seats behind the luggage rack. She claims that when the driver braked sharply, this caused a case to fly backwards off of a luggage rack in front of her and hit her head. As an expert in Newton's laws, you've been called to testify whether this story is credible or not. As part of your testimony, you will do a live demonstration in the courtroom, but you need to practice it and explain the results before you take the stand. Use the small block to represent the case and the top of the cart to represent the luggage rack in the bus. Devise a way to demonstrate what happens to the case when it is in the middle of the luggage rack at the moment that the bus stops suddenly. I did not prep for this at all. I should have gotten things in here, but let's see what's in this random room that we could perhaps use to do this simulation with. What do you know? There's a little weight in a bag of random stuff by this lecture desk, which will work quite. Oh, there's a dead bug in there from the last problem. This will work, I think, quite nicely for this demonstration. So here is the case, and we're going to put it on something. zoom out. Heck, let's just put it on our paper here. So what happens to that case when you actually move it? So I'm going to move it and then I'm going to stop moving it. I don't know if you can see that in here. So if you get it up to moving speed and then you stop it, the thing keeps on moving in the direction of motion for a little while. So if I'm moving it and then I stop, it slides forward a little bit. It's more dramatic if you do this with something that has larger mass to it. I don't know if there's other objects I can get to work better here. So anytime you have it moving already and you stop, the thing keeps moving in the direction that it was moving for a little while, which is important to this particular scenario. So describe how you conduct the courtroom demonstration. You would do something akin to that, but basically they give you a scenario of a lawyer conversation between the two lawyers. So you're saying that a backward force acts on the cart so it stops moving, but as it does so, a forward force also acts on the block so it is pushed to the front of the cart. Lawyer 2 says, I disagree with my colleague. I think that what you are saying is that a backward force acts on the cart, but no force acts on the block, so it just keeps moving forward at the same speed while the cart stops. Which lawyer do you agree with, or do you agree with neither of them? Well, consistent with the ideas in this activity, lawyer 2 is more correct. There is nothing that is pushing the object backwards, but you do not need to push the object backwards if it is already moving. If it's already moving, the forces on it, and it's moving at a constant speed, the forces on it are considered to be balanced, and you don't have to do anything. It'll just keep moving in that direction at that speed until you have some sort of unbalanced force acting on it. So while the bus was my bus here, I guess my page was my bus, right? So while here's a cart. When the bus stops moving, I don't need any force on the case for the case to keep sliding forward for some period of time, which is more consistent with the ideas of lawyer 2 here. Finally, the block does stop when it reaches the front lip of the already stopped cart. Why is that the block now stops rather than stopping at the same time as the cart? Well, if this thing slides across the cart until it hits the front lip, that front lip is the first time that it encounters a backward force on the case, which is what you need in order to change an object's speed and to slow it down if it was moving in the opposite direction as that force. All right, so finally, write a scientific explanation. And so this is one that throws people a little bit when they're doing this usually, but the force diagram in its simplest form is actually quite easy here. You have the bus. I should know how many wheels are on a bus. I don't. So there's the bus. And if a bus is going to stop, we'll assume the driver takes their foot off of the gas, puts their foot on the brake, and so there is nothing pushing the bus forward any longer, but there is a friction force on the bus by the road. And the bus is moving in that direction. That's really all you need to explain why the bus stops. There is the bus moving in one direction, an unbalanced force, in this case a force opposite to the direction of the bus's motion, and that's going to cause the bus to slow down and stop. But the case that is sitting up there on the shelf of this bus is moving along with the bus, but there's nothing, and I think they tell us to ignore friction in this situation, there's absolutely nothing that is pushing backwards against that case. And so this is actually the right force diagram, which throws people a little bit. I don't actually have to put any forces on this force diagram. Now, there are vertical forces on this case. There's a force from gravity. There's a force from the shelf it was sitting on, but there are no horizontal forces on here. So the explanation goes something along the line of a bus and case are in motion down the road. When the bus driver puts on the brakes, this creates a force from the road on the bus that is opposite to the direction that the bus is moving, this unbalanced force will cause the speed of the bus to decrease. At the same time, there is nothing that is providing a force in the direction of motion or opposite to the direction of motion on the case, and so the case remains in motion, moving forward through space until it encounters something that gives it a backward force to stop it. And so if you look back at the little picture they give us here, right? Here is the woman suing the bus company. Well, this case, if the bus is stopping, the only possibilities are for the case to continue forward at a constant speed, or if there is friction between the case and the shelf, the case will continue forward at a constant speed, but there will be a friction force on it that is slowing the case down. However, there is no scenario as described that would cause the case to come backwards and fall on this woman. But this does close with, where are we at? Suggest some circumstance under which the passenger's claim might be credible and briefly explain why. Well, the only situation that is going to lead to that case coming backwards is if both the case and the bus were already moving in that direction to the left. So if the bus were backing up and stopped suddenly, then it is plausible that the case would continue in motion, fall on the woman, give her a lawsuit, etc. So that's the only scenario in which, well, that's not true. That's not the only scenario. The other scenario is bus and case start at rest, right? The bus, they've souped the bus up. It can accelerate really quickly. So you start driving the bus and it speeds up really quickly. That's another situation where if there's not sufficient friction between the case and the shelf, this case, which hasn't been in motion, if it doesn't have a force to cause it to change its speed, will stay not in motion. And the case, the bus could move forward, the shelf is connected to the bus, and the case could possibly fall. Again, if I put this on a piece of paper, but I very quickly remove this piece of paper, this case can stay in place, and if the shelf is gone, it could have possibly fallen on the woman. So I guess the two places where the passenger's claim might have some merit is if the bus were backing up and stopped suddenly, or if it started from rest suddenly, but no bus I have ever been on has that kind of acceleration.